Document status, so we have pretty much 2 working group documents and another one which is not on the slide. So the first document, the GREMT document, we just requested publication. So Ted was our AD and it went on his plate, but the working group is changing hands to Brian. So we also briefed Brian now that like it's on his plate now. Okay, so that's it's gonna start moving soon with AD evaluation. And the other document is like the IPv6 GRE document, which got adopted since the last meeting. So it's gone through like 2 revs already, and it's been actively discussed. And so Ron is going to present like the updates and see what the working group thinks. So as you see, the agenda is pretty tight, and so keep your questions to minimum, pretty much. So like keep it short, and then other stuff we can discuss on the mailing list. So we'll let Fred get started.
Okay.
So, excuse me. So any agenda bashing? So anybody has issues with the agenda or? Okay, cool.
One.
Fred, go ahead.
Wrong one.
Okay. It's the one that says 2.
Okay. Okay, next chart. So what we see about tunnels is that encapsulation headers always consume data bytes. So that breaks the 1500 everywhere assumption that seems to be prevalent in the internet today. And it's exacerbated by tunnels within tunnels where we have even further levels of encapsulation. Tunnels perform link adaptation per RFC 2460 when the MTU is insufficient. So link adaptation is a way in which a box can break up a packet into pieces that'll fit across the link and be reassembled at the far side. Next chart. To uphold the 1500 everywhere assumption, one strategy a tunnel ingress could employ is that it could say anything smaller than 1280 minus in caps we can send without fragmenting because it's guaranteed to fit within the 1280 byte minimum MTU. Anything larger than 1500 bytes we can send without fragmenting because hosts that send packets larger than 1500 are really supposed to be doing RFC 4821. In other words, sensing that those packets are getting through without being dropped by a black hole. Anything in the middle zone, though, that's larger than 1280 minus in caps and less than 1500 might have to use fragmentation to get them through and probe to see whether fragmentation is still necessary. So if fragmentation is needed, though, it'd be nice if we could somehow tell the original source that, hey, your tunnel's fragmented. It'd be nice if you could back off and either limit the size of the packets you send or do the fragmentation yourself. And this is what I'm calling an advisory packet too big. Next chart. So what is an advisory packet too big? When the tunnel has to fragment, it can send a packet too big with a size that's smaller than 1280, subject to rate limiting. It can then either discard the payload packet and treat the packet too big as a loss indication, or it can fragment the delivery packet and treat the packet too big message as an advisory indication. So when a source gets this packet too big message that lists a size smaller than 1280, the RFC says it must include a fragment header in future packets, but it need not reduce the size of the packets it sends below 1280, and that's per RFC 2460. Unfortunately, not all sources do this, and also sources that don't do it are non-compliant. So the source could, instead of doing that, reduce the size of the packets it sends to a size smaller than 1280, or it could fragment future packets that are no larger than 1500, so the tunnel ingress doesn't have to fragment. So that's the results of what an advisory packet too big could cause a source to do. Next chart. The tunnel ingress options: when a source sends an atomic fragment, an IPv6 packet no larger than 1500 with a fragment header, but with more fragments set to 0 and offset set to 0, the tunnel ingress can either fragment the payload packet into 2 packets, then encapsulate and send both, and they'll be reassembled by the final destination, which is required to reassemble 1500. Or it can perform tunnel fragmentation on the payload and encapsulate and send both fragments in separate delivery packets. And these fragments will be reassembled at the tunnel egress, but the ingress needs to know that the egress can reassemble this much. For example, it needs to know that there's at least a 2K byte minimum MRU on that side. Or it can encapsulate the payload packet, then fragment the delivery packet, and these fragments will again be reassembled by the tunnel ingress. Next chart. So for non-IP encapsulations, we might have, for example, IP-GRE Ethernet encapsulation where Ethernet needs to see 1518 bytes. And there is no such thing as a packet too big message in that environment. So that means that the egress must be able to reassemble at least 1518 plus in caps, and that fragmentation can't be avoided in all cases. So that we might also actually need sizes larger than 1518 for some IEEE encodings. Ethernet within Ethernet encapsulations is another gray area. Next chart. So documents of interest, we have this draft template 6-man link adapt, which is talking about the advisory packet too big messages. Draft template arrow link and arrow min. Also the Intarea GRE IPv6 document and draft Herbert GUE. And that's my lightning delivery of this talk on advisory packet too big messages. Questions?
Okay. There's no question. So what's your goal, Fred, with this? Like, do you intend to, where do you want to work on this? You want to work on this here, or like, what's the goal?
I'd like to bring it into this group for discussion, and I think I can take it to the mailing list and try to generate some discussion on it.
Sounds good. Thanks.
Okay. Thank you.
Ron?
Okay. Second lightning presentation. We were working on a draft a couple of months ago that talked about IPv6 payload over GRE and GRE over IPv6, and somebody pointed out that there's no standard for either. So we decided to remedy that. Next slide. So we wrote a draft. Last IETF, it was adopted as a working group item. We got lots of conversation on the mailing list between these two IETFs from Fred, Joe, Lucy, and Tom Herbert, and we had a few changes which are summarized in the next two slides. First is checksum text. When the delivery protocol is IPv6, the GRE ingress should set the checksum present field to 0. The GRE egress router must accept a value of either 0 or 1, and if the GRE egress receives a value of 1, it must use that information to calculate length. However, it's not required to use it to calculate packet integrity. The next change, next slide, had to do with the MTU, and it is basically what you do when you're in a situation where fragmentation might be required. When the GRE ingress receives an IPv6 payload whose length is less than or equal to the GMTU, the GRE ingress must not fragment the payload or delivery packets. That means if you don't need to fragment, you must not. Now, when the GRE ingress receives an IPv6 payload whose length is greater than the GMTU, it means fragmentation has to happen, and the GMTU is greater than or equal to 1280 octets, the GRE ingress router must discard the payload, send an ICMP PTB back to the origin, and let's say, whoops, those bullets shouldn't be there, and the MTU field should be set to the GMTU. So what it's saying is, in that nominal case, where the GMTU, the MTU across the tunnel, is greater than 1280, drop the packet, send an ICMP PTB back to the source. Next slide. And when you need to fragment and the GMTU is less than 1200, then you have a choice. By default, you drop the packet and send an ICMP packet back to the source. However, you have a configuration option that is on the ingress that says, rather than doing that, I'm going to fragment the delivery, encapsulate the payload in a single GRE header and fragment the delivery header. The default behavior is to drop the packet and send an ICMP back to the source. The non-default behavior is to fragment the delivery header. Next slide. So, it's a painfully short draft, all of 6 or 8 pages, lots of discussion. We'd like to ask for a working group last call, but we have lots of comments. Eric.
So, Eric Nordmark, so did I read your slide, your previous slide correctly, that you said the default is to throw those packets away, even though they're perfectly valid packets?
Yes, the default is to discard them and send an ICMP back.
But the host will ignore that because it's less than 1280.
Yes.
So that's no service.
That's true. Now, the
But,
question
I mean,
is...
I don't have a problem with the knob. I have a problem with the default setting. But
Yeah, I see. That's what we're arguing about. Which is the most likely scenario? I'm thinking that it's such an odd situation to have a GMTU less than 1280 that maybe you want to think about what's going on. But maybe if it's not so odd, the default configuration is backwards and it should be the other way.
well, yeah, I think because you basically are telling the host that me as a provider of the tunnel, I'm screwed up, but I'm telling you that I'm screwed up, right?
Mhm.
Because my GMTU is too low, right?
Okay.
And you're supposed to tell yourself, not tell the host, because the host can't really do anything about it.
I'd be perfectly happy to switch which behavior is the default. Looking
Okay.
for input from the working group. Just tell me which and I'll make it happen. So I'd like a few people to come to the mic and tell
Yeah.
me which to do.
I had another one which you might have in your draft. So the GRE checksum is only for the GRE header, right? Is that how it's defined? I mean, the question is really about pseudo header checksum. For other things, one of the distinction between ICMPv4 and ICMPv6 is that we include a pseudo header checksum to deal with bit corruption in an outer IPv6 delivery header, right? Are you doing the same thing here? And would it make sense? Because it might be incompatible with how people do GRE over IPv6 today. I would be surprised if no one has already implemented. If no one has, whatever. I suspect people have already implemented GRE over IPv6, but I don't know.
Yeah.
No hats, but the GRE checksum contains the checksum of the header and the payload.
But yeah, my question is really about pseudo header versus not, and it might be that train sailed many years ago, which is fine.
Hi, Tom Herbert. I do have a question about the checks.
And Ron, would you mind, keeping
stand in the- sorry.
Yeah, square.
I had a question about the checksum. Can you go back to that slide for a second? So we had a discussion on the mailing list, and I thought the conclusion was that if the checksum is present, that the receiver must validate it. And that doesn't seem to be what you're saying.
Okay, well,
saying here.
actually, Suresh is the guy who answered that, so I'll let him speak for himself.
I think we should put that in. I think we should
So
add
if
the
it's
text.
present, okay, we'll make that change.
Okay, thank you.
Ole Tran. So for the GMTU, I think it would be a violation of IPv6 specs if you didn't provide a 1280 MTU for a V6 link. So you have to ensure that, I think.
I'm sorry, could you repeat that, please?
It would violate the IPv6 specs if you cannot provide a link layer that offers 1280 MTU or larger. So I think you have to ensure that. So I'm seconding, Eric's comments basically on that. With regards to the fragmentations, 2473 has quite a lot of text on that. Could you ensure that you are reasonably in line with that so we don't create two different ways of fragmenting, outer and inner payloads here? And thirdly, there are many implementations of, IPv6 GRE. Can we also do some work to ensure that we're not creating a spec here that is, not interoperable with the existing implementations?
Okay, I'll answer all three. So it sounds like we have two action items. First is to switch the default on what we do when the GMTU is small. Second is to say, yes, we will, if you receive a checksum, you must use it to verify integrity. Now the third, as for existing implementations, yes, there are existing implementations, and they do what the draft currently says. The default is to discard the packet. So yeah, we have a choice of doing what existing implementations do or do the right thing.
So I think you have to define that GMTU has to be larger, equal or larger than 1280, which might imply outer fragmentation here. And to the chairs, I think we would appreciate if you last call this, or at least notify the 6-man list as well when this goes through. Thanks.
So I mean, if there's a knob there, Eric Nordmark again, if there's a knob there and basically saying, yeah, existing implementations might not have that knob and basically be hard-coded to have it be in setting 1, right?
Well, the existing implementations have the knob. It's just the default value that we're arguing about.
Okay, yeah, that's sort of like, it's relatively easy for people to adjust their implementations, right?
Yeah. So what we'll say is the default value should be to fragment the delivery.
Okay.
Okay. So we will make those, actually it comes to 2 changes, changing the default value and checking the checksum. I'll submit the draft and then we'll ask for a working group last call. And also simultaneous last call and 6-man.
Exactly.
Deal. All done.
Thanks.
Next victim.
Please. That's a generic one. Tom?
Tom?
Hi, my name's Tom Herbert, and
Go into the pink penalty box. There's like a pink box over
in
there.
the box,
Yeah.
magic box. Step out of the box and you lose it.
The eject seat.
So I'm going to try to do another lightning talk. This is generic UDP encapsulation. It's a protocol, kind of what it says. Next slide, please. So basically, what we're trying to do here is a generic, extensible, flexible encapsulation mechanism. And this actually came out of network virtualization. However, we did realize that we could expand that and basically have a kind of a general protocol. Next slide. So generic UDP encapsulations, its roots lie in GRE. Protocol looks a lot like it. GRE, obviously well established, well deployed, very simple. So we like that in large deployments. Unfortunately, we've kind of hit a wall with GRE. Basically, it's really difficult to extend. So we found a way to extend it by somewhat overloading the checksum field and the sequence number field and the key ID field, but that's about it. And even if we added new fields on the edges, middle boxes that needed to do deep parsing wouldn't understand these new fields, basically because the GRE header length is computed by interpreting the field bits. So GU kind of you can think of as a successor to GRE or a potential successor. And in it we try to keep the same model of simplicity and extensibility. We want opportunities to extend the protocol, so that's a big part of this. And while we're at it, add a few improvements that you might have wished we had in GRE. Next slide. So this kind of a list of the features. As I mentioned, we'll use flag fields much like GRE, so if a bit's set, it refers to a field. We add a header length. This is a thing that allows middle boxes to basically skip over unknown fields to do deep parsing. The next header is indicated by IP protocol instead of ether type. We found a few interesting uses for that, and also saving those 8 bits from the ether type is actually worth it in the header. This is fundamentally UDP encapsulation, so it's much like the other UDP encapsulations. So we kind of get ECMP for free there. We have a concept of data messages and control messages. Security is a big part of this, so we actually define a security field, kind of optional, but this is used to authenticate headers in certain environments. Checksum, we have a checksum like GRE, although this is kind of the improved checksum. So it includes the pseudo header and it's UDP light, so that the checksum is only over the header. And this solves a problem in switches where they don't want to compute the full packet checksum, but still want to have some sort of checksum over the header. Hardware friendliness was considered. Obviously, GRE is hardware friendly by the fact it's deployed, and there are things that parse it. So we're kind of hopeful that that will continue. And as I mentioned, we have support for network virtualization. Slide. So I won't go into too much detail over the GU headers, but we have the normal version, header length, protocol next field. C bit indicates whether it's a control message or a data message, and then 16 bits of flags. And this last flag is actually kind of special. it allows us to extend the flags field so that we're not limited to 16 bits. We can actually extend that to another 32 bits. So conceptually, we do this over and over again and have as many bits as you want. So it is, trying to think a little bit forward. Hopefully we won't wind up with hundreds of flags, but it allows for that. Next slide. UDP, so as I mentioned, we can use a source port for entropy, much like other UDP encapsulations. UDP checksum, very similar to the MPLS over UDP, GRE over UDP. Same provisions, however, since we do have the ability to add a header checksum within the encapsulation, that may mitigate certain circumstances where we wish we could turn on the checksum, but we can't because of the switch compatibility. Next slide. So primary GU header, so I have some detail here. As I mentioned, there's a header length to allow skipping over protocol C-type field. Serves two purposes. Either it's an IP protocol or control type, and that's distinguished by the C bit. Next slide. So this is kind of an overview of the headers. I already mentioned that. Next slide. More on the C bit. Next slide, please. So I will mention about the flags. This is kind of an important part of the extensibility. And one of the things we're very careful about the flags is to make sure that we have forward compatibility. And one of the rules about the flags is if a flag bit is set and the decapsulator does not understand that flag bit, the packet is dropped. So this solves a lot of problems where if we want to add a flag, say for the checksum, receiver gets that and doesn't understand that, instead of just ignoring it and ignoring checksum, which would be a bad thing, it will actually drop the packet. So there is an assumption here of the ability to either synchronize or configure these things up front. And so you can kind of skip the next three slides. So this is some more detail on the flags and the fields and what we're trying to accomplish there. So the protocol is designed to be extensible, and in fact, we have already defined 5 extensions. Virtual network identifier is for network virtualization. This is really the only thing we found specific to network virtualization is that it needs this 32-bit identifier. Security field, as I mentioned, this is designed to allow either a security cookie, potentially a secure hash over the header. It is kind of a multi-length field to allow some expansion in the future. Header checksum, I already mentioned. Remote checksum offload is a little optimization. This is based on the fact that there's already a large deployment of network interface cards, NICs basically, that support UDP checksum offload, but wouldn't necessarily understand how to support something like GU. So there's a little trick where we can actually leverage these base UDP support of the outer checksum to offload the inner checksum. Tunnel fragmentation, I think Fred actually alluded to this. We actually came up with a design to do a tunnel fragmentation. This is kind of has some improvements over IP fragmentation. So for instance, we can do a 32-bit identification instead of 16-bit identification. So that's kind of promising. There are a number of potential possibilities here. And I think this is like a normal, what are the value here? We're trying to make sure that anything added is as generic as possible. And in fact, some of these fields like a virtual network identifier security field can be defined in such a way they can be reused. So for instance, security, we could have a 64-bit field, but you could use different algorithms for that. And we don't have to specify that up front in the definition of the security field. So it's kind of like repurposing the GRE key ID. We can extend that model to some other fields. Next slide. Private data region. So this is another feature that we added kind of to enhance GRE model a little bit. This allows, after the last flag and before the payload, if there is space in there determined by the header length, this can be arbitrary private data that is inserted by the sender and understood by the receiver. So it can be any structure. We have one case where people are putting TLVs in there, whatever, and so it's fine. So that's kind of neat. Next slide. The status. So we have three primary drafts, plus a few that describe some of the extensions. The GU draft is the base draft, and that describes pretty much the protocol as is. The network virtualization draft is specific, or the NVO is specific to the network virtualization extensions, and we have a security draft describing the field. We have a port assignment. This is now in upstream Linux, so you can test it out if you wish. We actually support IP over GU, GRE over GU, SIT over GU. So one of the reasons why I wanted to come today, actually I had a question. Basically, which working group should we consider this to be in? So I think that's one of my fundamental questions. I have asked for adoption in NVO3, and that's going pretty well, but unlike some of the other protocols in NVO3, this is really intended to be a generic encapsulation protocol that supports network virtualization, as opposed to a network virtualization protocol.
Okay.
So thoughts?
So you have a question? Yeah.
Well, Juan Carlos Zúñiga no had questions. Did you attend the SPUD or SPUD both on Tuesday when we were discussing this from the privacy point of view, this idea of hiding information?
SPUD BOF?
Yeah.
Yes, I was there. And yes, I do believe this could easily kind of be contorted to do transport encapsulation also. So before that, we only considered the tunnel encapsulation. Mm-hmm. This is very similar to SPUD, and in fact, I think there are some things we do need that SPUD mentioned, like that magic number to allow middle boxes to positively identify that this is actually encapsulation so it can parse it. So I think that would be a good addition. But if you kind of peel back the onion, these become very, very similar at some point, if not the same. For instance, one other thing we need here is probably DTLS. The original security draft said IPsec, but I think DTLS is much more compelling with the UDP-based protocol. So we'd probably have that, in which case the packets would probably almost look identical. You couldn't tell the difference between a tunnel and a transport encapsulation. If the payload's both encrypted, all you have is some sort of encapsulation header. I don't know if that was your question, but
well, yeah.
That was
I
my
wanted to see
inference.
what is there, because definitely there's a lot of relationship or overlap or
yes,
need for coordination.
I did mention in the
right?
SPUD that there's kind of parallel efforts here, and a lot of this comes back to UDP encapsulation.
Right.
There's a lot of commonalities, and we should try to leverage that.
Okay, thanks. But
Yes.
Besat, go.
Yeah, Machad Sarikaya. My question is, I don't know if did you define a tunnel establishment procedure?
No, there is, the control plane is considered a higher layer. This is only describing a data plane.
The same thing that GRE people did, so, but it's well established control command line interface. You can create
I see. So
we can create a GRE tunnel, but I'm not sure how do you do with the GUI.
So,
I think it's a good idea to define the tunnel establishment procedure in the draft itself.
I see. So in one sense, it's similar to GRE. So I configure both ends of a tunnel and provide the parameters, and then I can talk GRE between them. There's other interesting use cases. So for instance, I think Fred's not here, but we have talked about the possibility that Arrow would actually use GU as the underlying encapsulation. And then the management of the tunnels would be Arrow. And from that point of view, we consider kind of Arrow, or in the case of NVO3, network virtualization, to be the user of the encapsulation, and the control plane is deferred to that layer. So there's a clear separation here between data plane and control plane. So I don't think we're quite really punning on that. I think it actually makes sense to have this separation. Keep this as just encapsulation, properties of encapsulation, and then above that.
But then people who want to use it, they have this problem, right? How do I establish? So then everybody will come up with a different protocol. So isn't that a problem?
Well, like I said, I mean, we already have GRE. We've lived without having a control plane for GRE.
GRE is well established, and almost every router vendor, I think, they support command line interface for that.
So what I would anticipate would happen is there will be another layer, either Arrow or some generic tunneling kind of control layer, network virtualization control
Maybe we
plane.
should write a draft about it.
Yeah, so we'll have to get to that too.
So I went through the draft, but you said like we had like extensibility issues with GRE, right? Like it's not clearly defined. What did you want to extend with GRE that was difficult?
I can give you the precise example and why we actually invented this at Google. It was a response to our attempts to turn up network virtualization. So with network virtualization, we needed a protocol, and the one requirement that we had that wasn't satisfied by any existing protocols, VXLAN or NVGRE, was we needed a security token. So we needed to prevent a mechanism to prevent anti-spoofing, basically, and guarantee the integrity of the virtual network identifier. The problem was if the virtual network identifier became corrupted, packets could go to the wrong tenant. This is a serious breach of kind of our first requirement, network virtualization. So we have to add something. GRE is the most common, probably most commonly deployed encapsulation. We would like to extend that. But GRE, besides the key ID, really doesn't have any usable fields that we could put the security in. We could try to hack it and overload some of those fields, but pretty quickly, even if we managed to do that, well, we still would like a header checksum. So GRE checksum, very limiting, right? It's just the payload, doesn't even have a pseudo header checksum. So can we have a header checksum? That was actually one of the suggestions from the fragmentation and tunneling problem. So you start to go down that path and realize, wow, if we're going to create a new protocol, let's make sure it's extensible, okay, and hopefully last 30 years, and we can predict, we can even meet the requirements in the future we can't predict for something like this. Okay. Security, I think, is a big one. Security is only going to get tighter and tighter in the data center, so we're going to need more and more opportunities.
Okay, so Juan Carlos next, and then.
Okay. Sorry, I put myself in the queue. Juan Carlos Zúñiga again, NOHAT. There's two aspects to it. One is the network or the virtual network identifier, and then there's also the privacy. So my comment goes more towards the privacy, and I want to get to your question to what working group should this be in. There's several efforts right now going on the privacy. Like we're running this MAC address randomization experiment, layer 2, but then there's also drafts for IPv6 address privacy settings. Then we're talking about doing this in IP layers 3, 4, but also we have talks with W3C on the higher layers. Seems to me that we actually require quite a bit of coordination and make sure that we do the right thing when it comes to privacy features. And I'm not sure at this point in time one single group can answer the question. We just talked about the spot, the overlap with spot, and the fact that there could be some overlaps or relations or need to coordinate, let's say, between the two.
So I agree with that. In some sense, it would have been nice if we could have put this into either IP options or IPv6 extension headers, but then we run into the common problem, again, switch support for these. And so I know Eric probably has feelings about this too, but one thing about an encapsulation header, in theory, we can solve problems like that, right? So we could never extend IP options because switches don't support it, but we could start to put this stuff in encapsulation headers. I'm not advocating that. I think it's a slippery slope. So we definitely need a lot of diligence about where we put these things. In this case, the security actually is tightly associated with a virtual network identifier. So I'd like those to be logically together, that they are one and the same. I cannot accept the virtual network identifier without the security saying it's valid. So there was a tight coupling to this. And there may be alternatives, but this was actually pretty simple to just put them in the same header.
How do you ensure the trust relationship with the network, or there's an authentication to the actual network? Because then, if you are binding the two, then you need to have the mechanism to also make sure that the network is trustworthy.
For the network to be able to parse?
To the virtual network, yeah.
So the rule is middle boxes may inspect the headers. They do not have to understand all of the bits. They should not drop it if they don't understand something. They can inspect it. However, they really can't change it, and security probably prevents that because security is end-to-end, so if they change the bits, it'll break the security. But we do allow for middle boxes to parse this. If somebody wants to firewall based on the virtual networking identifier, which is almost, I mean, it's pretty much guaranteed to happen, then yes, they can do things like that.
Okay, thanks.
Eric, go.
Eric Nordmark. So I think that on the extensibility thing, unless I'm mistaken, but I thought that the reason to have the header length is not only for the middle boxes, it's also so that you can potentially send a packet with some new stuff in it, and the decapsulator can basically decapsulate it and sort of silently ignore whatever it didn't understand, right? Which we can't do with GRE.
On the decapsulator, you mean?
Yeah. I mean, it can say, I know about flag 123, and that's all I know about, so I can actually parse that and decapsulate it. The fact that the encapsulator included, oh, it's over there, included flag 4, right? The decapsulator can skip that. Isn't that the default behavior here?
No, it's the exact opposite. If the decapsulator gets a flag that it doesn't understand, it must drop the packet. And the reason for this is the forward compatibility problem, and I think we're seeing this in VXLAN. Another instance is the router alert. So if I add something like a security field, and that's a new field, and I send that to someone who doesn't understand that field, it makes no sense to ignore that. You're basically ignoring a security field. So if you look at the extensions we've added, I haven't seen one yet that would make sense to ignore. There may be some, but for the most part, you know, if we had something in checksum, or if we had something like remote checksum offload that is supposed to modify the packet to fix up the checksum, we really can't ignore that. We certainly couldn't ignore fragmentation because this is no longer a packet that can be received by the host. So there may be alternatives, and we can take it offline, but even GRE had some semblance that some of the flags can't be ignored and some can be. I'm not sure how successful that was in GRE.
Yeah, I wonder whether we want the flexibility of having some that sort of ignore if you don't know about them, but we can take it offline and see. Because it's a bit.
I would really love if somebody gave a good use case for the ignoring flag problem. I do realize that this is, in some sense, contrary to a lot of precedent. GRE was a different one, and that have mandatory flags. But input on that would be great.
At some level, I mean, I'm reflecting saying, and this is just reflection, but it's sort of the inverse of today. Today, the middle boxes will drop everything they don't understand, or many middle boxes have that behavior because they think they know everything, whether we told them to behave that way or not. And the endpoints are sort of more liberal in what they accept, and this is sort of the opposite. But
I don't know how to respond to that.
Okay, thanks. So I have a use case like for this, like it's incremental deployment, but let's not talk about it, right? Like, so we need to first figure out like where this is going to go, right? So what is the status of this at NVO3? So because I don't see anything in the tracker that there's an adoption call or anything, so.
So we are in call for working group adoption. Okay. That's been going on for about a week, so we're halfway through. So far, all 3 of the proposals have not had any negative feedback.
Okay, so.
And I did mention to Benson, so I suggested this. I said we have 3 drafts. What is the appropriate place? And he said to ask the in-area guys.
Okay. So, Brian, have you had a chance to take a look at this draft? Okay. Okay. So I think Eddie Bryan, yeah. So, so I think it's like worthwhile discussing this in the Intarea mailing list. So let's try to get a discussion going on the mailing list to see if it like belongs here. But if NVO3 is willing to take up the work, we can just like last call it here, like Ola was suggesting for the GRE draft. So if there's like another place where it fits and nowhere else where it fits, right? If there's no other working group that wants this other than NVO3, it makes sense to leave it in NVO3 and we can just do review here. So that's one way to go forward, right?
Okay, so I would like to keep them as separate drafts because I like the modularity of the definition.
Okay, Brian?
Brian Haberman as your newly ordained shepherding AD for less than 24 hours.
Welcome.
So, yeah. I guess there are two aspects here that I want to make sure we keep in track. The first one is, and forgive me for having come in here late because I'm actually chairing a working group somewhere else. The routing area is hosting a design team to try and figure out all these data encapsulation mechanisms. Okay, I just want to make sure that we're on board with that one.
I'm on that committee.
Good. Because I don't want Intarea to go running off doing yet another data encapsulation mechanism and have those guys go, what are you doing? But as long as you're involved, I'm fine, and that lets everybody here know what's going on. The second thing is that I think at a minimum you want to have people here review it. So if NVO3 wants to adopt all three of them, then as things go forward, I would expect to see a kind of a dual working group last call in both Intarea and in NVO3. Having not seen these three, are they? I mean, I assume that the second two are NVO3 specific, and the first one is a generic.
Technically, only the NVO one. The third one is actually generic. It's security for the encapsulation.
Okay, but they all need to go together, right? Or
I believe so.
Okay.
Security is optional. However, I believe it's kind of core, at least to everything that I'm thinking.
Oh, let me channel Stephen Farrell. Security is never optional now.
Thanks, Brian. Dave?
David Black, wearing a transport area working group hat and trying to walked up here with sort of a explanation of sort of where transport is, and I think overriding concern is there probably ought to be one focal area for this work, and right now, I guess I agree with what I thought I heard Brian say, that the routing folks appear to be leading the charge there. I mean, I've talked to Tom about this draft a few times. I've seen NVO3. I think NVO3 is going to adopt all of these. Over in transport, I think we're going to care somewhat about the use of UDP, but in particular we have the GRE and UDP draft, which we're making progress on. I think this is okay to go forward if you've got something generic, but I'd hate to go see things getting worked on in different ways in different areas. And my sense right now is that routing is in the lead, and I'm happy to have things stay that way for a while.
Okay, thanks, David. Eric?
So I agree with that. I think the thing that we can, if there are other use cases that are not tied to NVO3, right, it might make sense to discuss those use cases here, right? Because you can't really discuss them over there, right? And, I don't know if, some of them you already covered, but if people come up with additional ones, that might be one of the things that would be closer here than in NVO3. I don't know.
What do you mean by use cases? So,
like, I want the fortune cookie option, right? Something else in the packet.
Okay, not use cases of the protocol, but
additional
extensions.
Yeah, extensions, whatever, right?
Uses. Okay.
Yes, that's what I meant. Yes.
Okay, that makes sense. So there are a series of drafts. So, for instance, the fragmentation option is probably of less interest to NVO3, but seems like it would be more interest here. And
yeah, that's a good point. Particularly if we're talking about other aspects of fragmentation here in tunnels, right? That might belong here, but I don't know. Yeah.
My inclination is, and correct me if I'm wrong, to start with the basic three and then move to the rest. Okay.
Yeah.
Thank you.
Okay, so thank you very much, Tom. So what we'll do is we'll take the discussion on the list and talk to the NVO3 chairs and the routing NCAP design team head. That's Eric over there. So since David Black doesn't want it in TSP for now, so let's get started from there and see where we want to take this. Okay, thank you. Denghui?
Yes, I'm here. Okay, so So it's my fault I didn't apply the time slots for the MIF working group for some reason. So here I think maybe you are not the really the MIF working group people, but I have to make a short presentation. So what MIF today is we have the architecture working group draft is in the RFC 8Q, so Ted has approved in this week. And we also have the MPVDID. I believe that's been presented a couple of times. We are thinking we are going to have a working group last call after this meeting. And also we have the DCP support MPVD extension that has been presented in DCP working group. I think they got comments, we are update, and after the update we are going to have last call together. And also the NDP extension also been presented in the 6-man working group. We also got comments and we will be update together. And also so these three drafts will be we are going to issue a working group last call before next IET meeting. And the first one is the MIF API document. So we plan to have rewrite this document to adapt to the MPVD architecture. So we would like to have the major contributors work on this. And the chair will coordinate the offline people about this work. And the third one is broadband forum liaison work. So the MIF working group has an interest to work on this since last IET meeting. And we have got some of the volunteers, and we are thinking we probably, as one of the candidate proposal from IETF to work on this problem, we are talking with ADs about what we are going to do next. That's it. Thank you.
Thank you. Lishan?
The topic is DCPv6 options for the discovery of 464-XLET IPv6 prefixes. And the 464-XLET provide IPv4 connectivity across the IPv6 network using translation technology. And in the translation process, the CLET must discover the PLI set translation IPv6 prefix. CLET embedding the destination IPv4 address into the discovered IPv6 prefixes to get the destination IPv6 address. And for the multiple PLIs scenario, different PLIs may have different IPv6 prefixes. In this way, traffic can be attracted to the correct PLIT. So our work proposes a DCPv6 based method for the PLI set IPv6 prefix discovery. And the solution is shown as a finger. First is the CLET and DCPv6 server interaction. The CLET requests the PLIT prefix list option in DCPv6 request, and then the DCPv6 server provisions the PLIT set translation IPv6 prefix list by the option, and then in the list the PLIT IPv6 prefix and one or more PLIT IPv4 prefix it serves are all contained. And the CLET records the PLIT side translation IPv6 prefixes. In the translation process, the CLET must select the correct PLIT. According to the provisioned prefix list and the destination IPv4 address, the correct IPv6 prefix can be selected by the longest match first rule. Next. And there are two options defined. First is the PLIT prefix list option. It is a container option for one or more PLIT prefix option. and it is compatible with the single P-light if there is only one prefix in the prefix list. And another defined option is P-light prefix. It is encapsulated in the P-light prefix list, and each P-light V6 prefix comes in its own option. In the option, the P-light IPv6 prefix and the corresponding one or more IPv4 prefixes are all listed. Next. And comments are welcomed, and I wonder which working group is fit for the draft.
Okay, so just to provide everybody some background, 464XLAT is a transition technology that was worked on by V6Ops. And V6Ops is not chartered to do protocol work, okay? And it's a DHCP option, but DHC working group doesn't do options for other people. It reviews the options at some point when people do protocols. And so that's why there's no natural fit for this work. So that's why we are considering this in Intarea. So just some background. So now any comments? Okay, I think we'll just take this up on the list and see if you want to adopt it here or not. Okay, thank you. Eric?
I thought this rectangle was, sorry, the shape of the rectangle's off. Need to realign it. So I decided to come up with a long title. So it was brought to my awareness that we've run into these various things that I decided to call intentionally partially partitioned links, for a mouthful. There's actually just one slide. You can go to the actual slide. And I'm trying to investigate this stuff, and I'm basically standing up here saying, if you have some clues to impart on me or you want to help with this stuff, let me know, right? But I'm planning to sort of gather some stuff into some internet draft, but I haven't started that yet. But I just want to, I got this opportunity to send this advertisement or whatever, request for help. So these links are, they look to IP as a link in that they have a subnet prefix, but they're intentionally not uniformly forwarding packets at layer 2, right? And we've seen, so typically the way they used is that hosts can talk to routers and vice versa, but hosts cannot talk to hosts. And we've seen at least 2 examples of this, or I've seen 2 examples of this. There's a split horizon case that's used for DSL, where basically the hosts can't chat with each other, described in some DSL forum report. And there's private VLANs that people deploy to sort of conserve on connectivity, address space, whatever. There's a solution, or there's very little written down how to deal with this stuff in the general case, as far as I know. Sort of how do you configure things and what works and what doesn't. We have a solution for the specific case of split horizon that deals with that, right? But I haven't seen anything that says how do you do ARP and ND for the general case, and in particular, how do you do DAD for the more general case? I don't think that proxy DAD thing necessarily works for the more general case, which is there in private VLANs, because a packet, you have these things that are, what is it called? I think it's called community VLANs, where some hosts can talk to each other and they can talk to the router. There's some other things that are somewhat related, which is some filtering in RFC 4562, which isn't really partitioning the layer 2 link. It's really saying, I'm going to play with the ARP tables and some filtering to get some isolation behavior. And I think, at least when I started thinking about this stuff, that felt like that was a different thing, but because it's not partitioning things at layer 2. So if you have clues to impart here, I'm grateful.
2 very quick things. One of them is you should add cable modem to the list.
Okay.
It behaves much in the same way.
It's split horizon, right?
It's split horizon, yeah. You basically, each connection to a subscriber is a separate channel. And so the subscribers can't talk to each other except through the CMTS. So it behaves a lot like DSL.
Okay. I'll
Okay,
definitely
so add that to your list. The other thing is that we've touched on this kind of thing a number of times before. You mentioned one, duplicate address detection. That was raised by the Broadband Forum in 6ops, and that's where that came from. Another one is really ancient history, frame relay, where you have circuits underneath, but it looks like a NBMA, non-broadcast multiple access network. And in OSPF, we wound up with a failure case and had to replace it with point-to-multipoint interface, which is essentially a bundle of circuits.
So these ones, at least, it looks to the attachment, at least to the host, it looks like a broadcast medium, right?
Yes, understood.
Yes.
So it's related, but yeah, it's a little different. You can actually see the circuit where, well, on a CMTS or a BRAS, you can tell that there is a channel underneath. Yeah, if you're actually on the BRAS or the CMTS. So at any rate, yeah, we do have some history there you might want to take a look at.
Thanks, Fred. And I'm inserting Andrew Yuchenko between Stuart and Dave. Thanks.
Stuart Cheshire, I have a question. This also sounds familiar, sounds similar to another case. If I'm sitting in a coffee house with the Wi-Fi access, I can't communicate with the person sitting next to me, even though we're on the same access point. Would that be another case that fits this model?
So there's two pieces here, I think. There's the L2 behavior, right? But then there's a separate thing. That doesn't mean that you can't communicate with TCP, because that's, as far as I can tell, sort of a ACL policy question on the actual router, right? What these technologies do is that they force the host to talk through the router. And then on the router, you can have, I believe, a policy saying, oh, this host can talk at layer 3, or I will run them through this firewall and see whether they can talk. And there might be deployments where people say, no, hosts should never talk, right? So there's two pieces to it. That it's the L2 behavior that basically fundamentally restricts communication. And then there's potentially L3 policies that further restrict things. But the implications for things like neighbor discovery, DAD, whatever, ARP, is due to the L2 behavior.
Okay, well, my two observations are, in many of the cases where this happens, it seems like the people running the network don't want the communication to happen. Maybe for misguided reasons. They don't want to be blamed for getting a virus on my PC, so they want to avoid the liability. My second observation is, if you do want the devices to communicate, that seems like a misconfiguration, because at least in my mind, the notion of a subnet, the useful property of a subnet is everything on the subnet is reachable by ARP, and everything that doesn't match when you use the subnet mask has to go through your default gateway. And if you really want to treat this as a series of point-to-point links, then don't make it look like a broadcast domain if it doesn't behave like that. So that it seems like...
Yeah. With a pure architectural hat, I would agree, but part of the reason these things were created was to save at least IPv4 address space, right? So it is a bit of a hack, but it's out there, and we should at least make sure. I want to do enough of an exercise to make sure that IPv6 works on them as well as IPv4.
Okay, I'm cutting the line at Juan Carlos. Okay,
and I think that requires sort of writing down how IPv4 works here as well. Yes.
Okay, so speaking for Andrew Yurchenko, it says almost any professionally done hotel event Wi-Fi is another example of this scenario, private VLAN. Nearly, if not all Wi-Fi vendors allowed to prohibit the communication between clients. And then he says something, okay, I replaced my previous comment with a comment to Stuart. I may want to save ND cache in a network with 10,000 hosts, and I may want to force hosts to communicate via router. So yeah,
force hosts to communicate via
router.
Okay.
Yeah. To save the ND cache.
Yeah.
Yeah.
Okay. So speaking for myself now, I would just like to say RC 3069, which is IPv4 for doing something similar. So you might want to reference that.
34.
No, 3069.
3069. Okay.
Thanks, Dave.
David Black. There's been a confusing multi-homing discussion in NVO3 that might result in the converse of the use case in your second bullet, where if in essence the L2 domain is hooked into the virtualization domain by more than one what are effectively routers, although they may not be. You can get in a situation in which you want the hosts to talk to each other, but you do not want something coming out of the virtualization domain via one interface going back in. I don't know where this is going. This discussion, I think, has been a bit confusing to date.
Okay. Yeah, I didn't quite understand that one, but I'll try to find out.
Just as point of order, we're out of time, so feel free to stay here and listen, but if you want to go, I'll understand. Thanks.
Okay, so Dave Thaler, I would suggest you do a compare and contrast, because I gather you're talking about what you would put into a document. A lot of the things that you're talking about are similar in some ways to the multi-link subnet model that's used by Mene, AutoConf, 6LoWPAN, etc. There's a couple differences, like the word intentionally as opposed to inherently by physics, and whether you are trying to preclude communication between hosts, or whether you'd kind of like to allow it if you could. And so compare and contrast, because a lot of the same issues are there, and whether you want to address them or not may differ. And so
Yes.
I would reference the multi-link subnet model and the 6LoWPAN style solutions to that for where you want to get around, for the issues and ways to potentially get around it should you want to. And it sounds like you're specifically trying to target the case where you want to preclude it rather than get around it, right?
At least precluded at L2, right? But yes, I
Yeah,
did
if
look
you're
at the
trying to-
multi-link subnet
If you're trying to
one.
preclude it at layer 2 and get around at layer 3, then it's just a multi-link subnet, and the existing techniques used by things like 6LoWPAN are applicable. Thanks.
I don't think it's identical, but yes.
So Juan Carlos Zúñiga. I also happen to participate in 802.1. There's a group there called OmniRAN Task Group, and one of the issues that we are trying to do is this network abstraction model for 802 technologies. And definitely one of the issues that we've been trying to coordinate, we are not at any stage yet, but some talks that we've been having, Brian Haberman was part of it, is how do we present 802 technologies to higher layers because of the issues that Stuart just mentioned. Like it's well known that some Wi-Fi interfaces, even though it's a multicast or broadcast domain, then you only have point-to-point communication because of artificial things that will make you get to the gateway. And this is especially true for the mobile now, that we are having this mixed nodes of like 3Gs or 4Gs and Wi-Fi's and so on. So just wanted to voice that there is this group in IEEE 802.1 that is trying to see how we can best serve IP from the lower layer point of view.
Okay.
We don't have an idea yet. We know there's several flavors out there, but it'll be interesting if ever we need something out of 802 or any coordination or any flag or any thing. Well, there's now
So is there
vehicles to get that.
some sort of digestible document that describes a bit what they're trying to do? I'm thinking about something to go read.
Well, in fact, the only document that it really gets into this specific point, because it's not the only thing that OmniRAN does, right? But for this specific point, we had a discussion about the NetExt logical interface that is an outdated draft that is been hanging there in the NetExt group for a few years.
NetExt logical interface. Okay.
And it was trying to describe how to at the time was for IP flow mobility and how we can basically present the same behavior from a Wi-Fi and point-to-point PPP 3G interface point of view to IP, so that IP wouldn't get confused. But still, that we were thinking about evolving that document into something more actual and wider than just cellular.
Okay.
But we can drop it and do something else if that's it.
Yeah, I'll go look at it. So.
Okay. Thanks.
Thanks a lot, folks. And thank you very much. We are 5 minutes over time, so thank you very much and have a nice evening. Enjoy your evening. Thanks.
And I will.
Well, that's So what do you want her to do? You want you're going to do it. Okay. So you'll post it. Or just know if you want to be.
Oh, yeah.